Kernel trick. Section 10.2 demonstrated that if the problem is nonlinear, instead of trying to fit a nonlinear model, we can map the problem to a new space by doing a nonlinear transformation using suitably chosen basis functions and then use a linear model in this new space. The linear model in the new space corresponds to a nonlinear model in the original space. This approach can be used in both classification and regression problems, and in the special case of classification, it can be used with any scheme. In the particular case of support vector machines, it leads to certain simplifications that we now discuss. Let us say we have the new dimensions calculated through the basis function z equals to phi of x where zj is equal to phi j of x, j starting from 1 to k, mapping from the d-dimensional x space to the k-dimensional z space, where we write the discriminant as g of z equals to w transpose times z, and g of x equals to w transpose times phi of x, which is equals to sigma of wj times phi j of x, summing for all j starting from 1 to k, where we do not use a separate double zero. We assume that z1 equals to phi1 of x equals to 1. And generally k is much larger than d, and k may also be larger than n, and there lies the advantage of using the dual form whose complexity depends on n, whereas if we used the primal, it would depend on k. We also use the more general case of the soft margin hyperplane here because we have no guarantee that the problem is linearly separable in this new space. The problem is the same. That is, LP equals to 1/2 times the square of the norm of W plus C times sigma of C to the T summing for all T, except that now the constraints are defined in the new space. R to the T times W to the transpose times phi of x to the T is greater than or equals to 1 minus C to the T. And the Lagrangian is LP equals to 1/2 times the square of the norm of W plus C times sigma of C to the T summing for all T minus sigma of alpha to the T times the term R to the T times W transpose times phi of x to the T minus 1 plus C to the T summing for all T minus another summation is sigma of mu to the t times c to the t summing for all t. And when we take the derivatives with respect to the parameters and set them to 0, we get delta LP differentiated by delta W is equal to W, and which is equal to sigma of alpha to the t times r to the t times phi of x to the t summing for all t. And delta LP differentiated by delta of c to the t is equal to the constant c minus alpha to the t minus mu to the t, which is equals to 0. And the dual is now LD equals to sigma of alpha to the t summing for all t minus 1/2 times doubling summations summing for all t and also summing for all s of the term alpha to the t times alpha to the s times r to the t times r to the s times phi of x to the t to the transpose times phi of x to the s, subject to sigma of alpha to the t times r to the t summing for all t equals to 0, and alpha to the t is between 0 and c for all t. The idea is, in kernel machines, is to replace the inner product of basis functions phi of x to the t to the transpose times phi of x to the s by a kernel function k of x to the t, x to the s between instances in the original input space. So instead of mapping two instances x to the t and x to the s to the z space and doing a dot product there, we directly apply the kernel function in the original space. LD equals to sigma of alpha to the t summing for all t minus 1/2 times doubling summation summing for all t and all s of alpha to the t times alpha to the s times r to the t times r to the s times k of x to the t x to the s. And the kernel function also shows up in the discriminant g of x equals to w transpose times phi of x, which is equals to sigma t summing for all alpha to the t times r to the t times phi of x to the t to the transpose times phi of x, which is equals to sigma of alpha to the t times r to the t times k of x to the t and x, such a pair, summing for all t. This implies that if we have the kernel function, we do not need to map it to the new space at all. Actually, for any valid kernel, there does exist a corresponding mapping function, but it may be much simpler to use k of xt, x to the t x, rather than calculating phi of x to the t. Phi of x and taking the dot product, many algorithms have been kernelized, as we will see in later sections. And that is why we have the name kernel machines. The matrix of kernel values k, where k ts equals to k of x to the t x to the s, is called the Gram matrix, which should be symmetric and positive semi-definite. Recently, it has become standard practice in sharing data sets to have available only the k matrices without providing x to the t or phi of x to the t, especially in the bioinformatics or natural language processing applications where x or phi of x has hundreds or thousands of dimensions. Storing downloading the n by n matrix is much cheaper. It's by the results of Vert, Suda, and Shonkov in 2004. This, however, implies that we can use only those available for training testing and cannot use the trained model to make predictions outside this data set.